Welcome to the second lecture in our Huntington Spring series. One of the things people always ask me, I'm an astronomer myself, and people always say, well, what do you work on? And I say one of the main goals for me, is to understand how the universe got into its current state. How did the universe go from the smooth Big Bang to what we see today? And largely what we mean by that is understanding how galaxies formed and evolved over time, how they changed. And so we have two lectures in our series that are going to concentrate on this very, very important problem. You're going to hear part one tonight, which is going to deal with the very early parts of the universe, right? And then we're going to pick it up in a month with Rick Williams on April 30th for part two, so I would encourage you to come back and hear that. But it's a very important topic, and it's one that we at Carnegie study quite a bit. So two lectures may not even be enough to cover this very exciting topic. Tonight's speaker is one of the newest members of the Carnegie family, Guillermo Blanc. Just finished his PhD last summer at the University of Texas, and he came as a prestigious Carnegie Fellow. I thought I would just spend a minute to just tell you a little bit about the Carnegie Fellowship, because it's a program that I actually run, just to say how difficult it is to get a position that Guillermo has gotten. We typically get about 150 applicants a year for our fellowship. There's 150 people who've mostly just finished their PhDs. So it's a very competitive thing. All those people, of course, are very good. They've got a PhD in astronomy. It's an extremely competitive process. And so to get this fellowship is quite an accomplishment. And many of our previous people at Carnegie are staff members, including our director, Wendy Friedman, are previous Carnegie Fellows. And so Guillermo is our latest, and we're happy to have him. And he's going to give us part one of this galaxy evolution.
All right. Well, hello. My name is Guillermo Blanc. As John said, I'm a new Carnegie Fellow at the Carnegie Observatories here in Pasadena. First of all, I'd like to thank the Huntington Library for hosting this talk and the Carnegie Observatories for having me here. And I'd like to thank you all for attending. I'm very happy to see so many people interested in the work that we astronomers do. So this, as John said, this is the first part of a two-lecture series that Dr. Rick Williams and I are giving on galaxy formation and galaxy evolution. And the idea of these two lectures is to tell you the story of how galaxies form and evolve throughout cosmic time. So galaxies, as you probably already know, are these huge complexes of billions of stars that are floating in space. And on top of having billions of stars, they also have massive amounts of interstellar gas and interstellar dust floating in between the stars. And they are basically the building blocks of the observable universe. When you look at space, most of space is empty or filled with very tenuous gas, but there are these bright spots in the middle of space, which are the densest parts, which is where galaxies live. And these are by far the most fun and eventful places in the universe. These are the places where gas actually gets turned into stars and planets form around the stars and life emerges around these planets, and even intelligent life seems to emerge in some of these planets. So these are I would say, the only fun places of the universe. And to understand basically where we come from, one of the steps that's very important is to understand how galaxies form and evolve, right? But galaxies, as I said, they're only a tiny part of the universe, and they live in a universe that's mostly composed of two mysterious components that we currently call dark matter and dark energy. So I'm going to tell you about how we came to realize that the universe is mainly composed by these two mysterious components, dark matter and dark energy, and because these two components basically drive the evolution of the universe and the evolution of galaxies, right? So, and when we talk about dark matter and dark energy, the word dark doesn't only refer to these two main components of the universe not emitting light or not putting out any type of radiation, but the word dark mainly refers to our ignorance. So we call them dark because we have very little idea of what they are and why they're there. But we have detected them, we know they're there, and we kind of know how they behave. And that allows us to model how the whole universe evolves and how galaxies form in it. So before I start, I want to start talking about one of the main challenges we face when we study galaxies and we study galaxy evolution, and that is the timescale problem. So if you ask the simple question, where do adult human beings come from, right? We all know the answer. We all know that adult human beings, right, old people come from young people, and young people, who are probably not at a Pink Floyd concert, right, come from children, and children come from babies, and babies come from embryos and inside pregnant women. We all know that, right? But there are two main reasons why we know that. One is that when we look around our universe, we look in our parks, in our schools, in our hospitals, in our streets, we see old people, we see young people, we see children and babies, and we see pregnant women walking around, right? So all the pieces of the puzzle are at our disposal, right? The other fact that allows us to understand this whole evolutionary process is that the time scale over which a baby is born and grows into a teenager and then gets old into an adult, right? The time scale is, pretty obviously, of the same order of magnitude as our lifetimes, right? So throughout our lifetimes, we can see this process happen live, right? So none of these two basic things happens with galaxies. When we look at galaxies, well, first, the lifetimes of galaxies are measured in billions of years, right? So in a human time scale, right, when we look at a galaxy, galaxies basically look static. They're not doing anything. Even though over cosmological time scales, they're maybe evolving very, very violently and rapidly. But for us, they just look static. We cannot see the process of galaxy evolution live because it takes billions of years to happen, right? And the other problem is that when we look around in the local universe, we see different types of galaxies, like the ones I'm showing here, right? And they all come in different shapes and they have different colors. But all of these galaxies that we see in the local universe have a significant amount of very, very old stars. So we're basically, when we look in the local universe, in the nearby universe surrounding the Milky Way, we never see newly formed galaxies, right? Some of them might be still forming stars, but they all already have a lot of old stars. So basically, we're surrounded by old people. We're at a retirement home, or we're at a Pink Floyd concert, basically, right? So we're surrounded in the local universe by old people. But the beauty about astronomy is that by looking further away, we can look in the past, right? And this is a very, very important concept. When the person who's in the back of the room, the light takes a longer time to get to my eye from the back of the room than it does from the person who's in the front row, right? So I'm seeing whoever's in the last row, I'm seeing him more in the past than I'm seeing the person in the front row, right? So if I look back at a distance of 1 million light years, I'm seeing galaxies as they were 1 million years ago, right? So we can overcome this problem of being surrounded by old galaxies by just looking further and further and further away, and in that way we look further and further back into the history of the universe, and we see galaxies and we see the universe itself at younger and younger epochs, right? So the outline of this talk is the following. First, I'm going to talk about what I call the way out. So I'll very briefly tell you about how do we find all these galaxies, how do we detect them, and how we measure their distances, and I'll tell you about the effort to find the more and more and more distant galaxies, to see how far back in the history of the universe can we look, right? Then the second part is going to be the way back, which is basically, now that we know we have observations of galaxies at different epochs in the history of the universe, what is our current understanding? I'll try to explain you what our current understanding of galaxy formation and evolution is. How do we think galaxies form in the very early universe and maybe evolve into the present-day objects that we see today? And then I'll also talk about what I call the way ahead, which is what is coming in the future, in the next 10 or 20 years. What are the new large telescopes and fascinating instruments that we're currently building to understand this problem more thoroughly? So the way out, right? So this picture right here, what you're seeing is a panorama of the whole celestial sphere. So this is a picture of the complete night sky reprojected the way you would reproject a globe into a planisphere, right, on the screen. So basically this point connects with that point over there. And this is the picture you would be seeing if you were floating in space, right, at the position of the Earth, basically. Anywhere you look, you see a lot of bright little dots, and you see this huge bright band, which is actually the disk of the Milky Way, the galaxy that we live in, right? We also see clouds of dust and gas that can actually block the light from the background stars behind them. But almost every single dot here that you're seeing, every single bright dot, is a star inside the Milky Way, inside our own galaxy. And you can still see a few other galaxies. So there are two bright dots over here. These are called the Large and the Small Magellanic Clouds. These are two small galaxies that are actually satellites of the Milky Way. So if we live in the Milky Way, the Magellanic Clouds are just orbiting our system, right? And down here you can see a small, faint smudge, and that is the Andromeda Galaxy. So the Andromeda Galaxy is a galaxy roughly of a similar size as the Milky Way, but much further away than the Magellanic Clouds are. That's why it looks fainter, right? And the Milky Way and Andromeda are the two main components, the two main galaxies in our local system that what we call the local group, which is basically the Milky Way, Andromeda, and each of them has their own satellites going around, right? Now, if you look very deeply into any point in here, and you start taking pictures that go deeper and deeper and deeper, you'll start seeing billions of little faint dots that are beyond our own galaxy and beyond the local group, right? And those are galaxies. So what I'm going to show you now is the following. I want you to imagine that you're floating in space, right? And you're seeing this picture all around you, right? And in your hand you have a grain of sand, something that's the size of a grain of sand, right? So you extend your hand and you looked into this grain of sand, and that defines a certain area on the sky, right? A small, very small patch of sky, right? So if you look into that small patch of sky and you had a very, very powerful telescope, and you zoom in into that very, very small patch of sky, I want to show you what you would see. You would see the following, right? So this image, which I'm using as my background, the background for all my slides, it's called the Hubble Ultra Deep Field. This is the deepest image ever taken in optical light, right? This was done by taking the Hubble Space Telescope and pointing at the same point on the sky for 11 consecutive days without non-stop. So you know how people who are photography amateurs here probably know that you can just adjust the exposure time of your camera to observe fainter and fainter objects, right? You just take an exposure that you expose your film or your chip these days, right, for a long time, and you just collect a lot of light. So this image was done by using a telescope in space and opening the shutter for 11 days, right? So it's really, really, really deep. And when you look at this image, you can still see some stars. So you see there's things like this over here, which looks like a little cross, right? There's another one down here that looks like a little cross. Those are still stars inside the Milky Way, right? That star right there is 150,000 times fainter than the faintest stars you can see with your bare eye, right? So these are very, very faint objects, right? And there are about 10,000 little bright dots in this image, and the large majority of them are galaxies. They're galaxies and they're all galaxies at many, many different distances, right? So there's these big things over here that are probably very nearby, but even the faintest smudge in this image can be a very, very distant galaxy, right? So now, the problem is, of course, you take a picture and galaxies are at different distances, right? So it makes no sense to do a map of the universe in 2 dimensions in a screen, right? So I'll ask the question, what does the universe look like when we make a 3-dimensional map of the universe, right? And we take all these galaxies and we plot them in their 3-dimensional positions, right? So this is what I'm showing you right here. So what I'm showing you right here is the the positions in three-dimensional space of roughly 300,000 galaxies that were detected by the Sloan Digital Sky Survey. This is a project that was probably one of the most important observational campaigns for galaxies that was done during the last decade. And it mapped a large amount of galaxies, and it was able to measure their position and their distance. And it has, out of this project, we have learned a lot about the structure of the universe. So here, what you're seeing here is a three-dimensional map in which this Earth, and basically the Milky Way, is sitting right in the center, right? And the reason galaxies seem to live in these fan-like volumes that you're seeing here is not because they really do in real space. There's not like an empty part of the universe, right? It's simply because what you're seeing is the positions of galaxies taking in a big image that only samples a little patch in the sky, right? So if you take a projection of that patch in the sky towards larger and larger distances, you get this fan-like volume, basically, that you are able to observe, right? So the most interesting thing about this map, right, is to look at exactly how galaxies are distributed in the sky, in the space, basically. They're not distributed homogeneously, right? There's not a smooth distribution of galaxies, but they rather seem to live in this filamentary structure, right? It looks almost like a sponge, where you have these big, large voids that are surrounded by these very dense filaments and walls that contain a lot of galaxies, right? So this is actually very important, because any theory or any model for how galaxies form and evolve throughout the history of the universe has to account not only for the formation of a single galaxy, but it also has to explain why galaxies are distributed in this large filamentary structure throughout space, right? So now we can ask, how do astronomers build a map like this, right? How do we go about finding all these galaxies and actually putting them in a map like this to be able to study the structure of the universe, right? So the first part is pretty easy. We detect the galaxies. You just take a very deep picture, right, with a big telescope and over some patch of the sky, and you just look for bright smudges, right, or bright dots, right? Now, that's easy. The very hard part is, how do you know how far away that is, right? Just look at a picture, like the one here in the background, and I have no idea at first hand of knowing if this galaxy is closer or further away than this other galaxy, right? So I want to talk to you about how astronomers go about measuring distances to galaxies. And there are many, many methods and different methods that astronomers have used during history to measure distances to galaxies. But I'm going to focus only on one, which is what we call the cosmological redshift, right? This is by far the most widely used method to measure the distance to a galaxy, right? And it's actually the only method that we use in the very distant universe, right? So the cosmological redshift is a tool that would not exist without the contribution of many astronomers, of course, but it's basically based on the discovery by Edwin Hubble back in 1929 that the universe is expanding, right? So Edwin Hubble, who is probably by far the most famous astronomer of the 20th century, lived here in Pasadena, worked at the Carnegie observatories, right? And he is credited with having discovered the expansion of the universe, right? So in reality, during Hubble's time, there were a few other astronomers that did similar work and reached similar conclusions to him, including George Lemaitre and Vestus Leifer. But Hubble's work was by far the most influential in the astronomical community, and he's widely recognized as the discoverer of the expansion of the universe. So what did Hubble do? How did he realize that the universe was actually expanding? So what Hubble did for a living was to use the 100-inch telescope on Mount Wilson here in Pasadena to measure distances to galaxies, right? So he was the first astronomer, the first person to show conclusively that what used to be called this spiral nebula, which are objects that appear in photographs of the sky, right, were actually extragalactic objects. That means that he was the first one to measure the distance to a galaxy and show that these galaxies live actually outside the Milky Way. And they are whole groups of stars by themselves and not simply objects inside the Milky Way, right? So Hubble measured distances to many, many galaxies. And by the same time, a few years earlier, there was another astronomer called Vestos Lieffer back in Arizona in Lowell Observatory who had realized, who had used a method to measure what's called the recession velocity of galaxies. So I'm going to explain you how this method works. But basically, you can use this method to look at a galaxy and see how far does that galaxy seem to be moving away or towards you, right? So what Hubble did was he took his distance measurements, he took this recession velocity measurements or radial velocity measurements from Vestos Lieffer, right? And he plotted them, and he realized that there was a linear correlation, there's a tight correlation between the distance at which a galaxy is and the velocity at which it seems to be moving away from us, right? So these galaxies are do not only seem to move away from us, but the velocity is tightly related to the distance at which they are, right? And the genius of Hubble was to realize that this was clear evidence for an expanding space, right? If a space itself is expanding, if the universe is expanding, you expect to see a correlation of this type. So just as a short example, I want to show you why this is, right? So imagine Hubble is sitting here in this universe that's filled of galaxies, right? And just to make things easier, I'm going to say that at a time 0, which is I call 0 hours here, every galaxy in the universe is separated by 1 kilometer, all right? So if the universe is expanding, right, we can think of a scenario, right, a scaled down scenario, of course, in which an hour later, let's say by time 1 hour, the universe has expanded in order to double its size, right? So now every galaxy is separated from its neighbor by 2 kilometers, right? So this is an expansion of space itself by a factor of 2 over 1 hour, right? So if Hubble were sitting here, he would see that this galaxy that's right next to him, which used to be at 1 kilometer away, is now at 2 kilometers away, right? So it moved 1 kilometer in 1 hour, right? And he would say the velocity, the apparent recession velocity of this galaxy is 1 kilometer per hour, right? But this galaxy right here, which used to be 2 kilometers away from Edwin Hubble, now sits 4 kilometers away, right? So in 1 hour, this galaxy moved from 2 to 4, so it moved 2 kilometers, right? So basically, the further away a galaxy is, right, you measure 1 kilometer per hour for this guy, 2 kilometers per hour per this guy, almost 3 kilometers per hour for this guy, right? The further away a galaxy is, the higher the velocity, the apparent velocity at which it seems to be moving away from us because of the expansion of the universe, all right? So this discovery had profound implications in terms of understanding the origin of the universe. The fact that the universe is expanding meant that in an earlier epoch, the universe had to be in a much denser space where everything was tightly packed together, and this gave origin to the theory of the Big Bang, right? This was the observational basis for the theory of the Big Bang. And it also had a very, very important physical implications, because it was one of the first empirical proofs of the validity of Einstein's theory of general relativity. So Einstein, about a decade earlier from Hubble, had proposed that, he proposed the theory of general relativity, and according to his theory, he predicted that it would be very, very hard to have a universe that was actually static. Most likely, the universe should be either expanding or contracting, right? And he went to... And at that time, most astronomers thought the universe was actually static. So he had to go to, he had to fine-tune his equations very, very accurately to be able to provide this static universe that astronomers wanted. So once Hubble discovered the universe was actually not static, but rather expanding, Einstein was very happy, because that's exactly what his equations predicted, right? So, but besides the profound implications in terms of the origin of the universe and the nature of gravity and general relativity, what's very, very important about this relation is that it provides a very, very useful tool to measure distances to galaxies, right? Because measuring the recession velocity, measuring how fast the galaxy seems to be moving away from us, it's way easier for an astronomer, as I will show you now, than measuring the actual distance to a galaxy. And you can do this fairly efficiently for many, many galaxies. So if you have a relationship like this, which is called the Hubble law, you can just measure the velocity, right, at which a galaxy seems to be moving away from you, go to this plot and say, this is the distance, right? Once you measure the velocity, you can actually derive the distance from this, right? And this method that we use to measure the distances to galaxies by means of their velocity is called cosmological redshift, or simply redshift. And the actual methodology that we use to measure this redshift is something that we call a spectroscopy. So a spectroscopy is one of the most powerful tools that astronomers have at their disposal, right? When you do a spectroscopy, you take light coming from an object, right? It can be from a light coming, for example, from a galaxy that you're collecting in the primary mirror of your telescope, and you can use some optical element to disperse and separate this light into light of different colors. So any beam of light in the universe is most likely composed of smaller beams of lights of different colors, right? And when you see that something is red, it's usually because it either emits or reflects more red light than blue light, right? And when you see that something is blue, it's because it either emits or reflects more blue light than red light. So a spectroscopy is a way of separating this light into different colors and see how much light an object is putting out at different colors, right? And now, light itself can be understood as a wave in the electromagnetic field, right? And the color of light is actually directly related to the wavelength of this wave. So red light has a longer wavelength or a lower frequency than blue light has, right? So red rays of light correspond to a wave in which the wavelength is very long, right? While bluer light corresponds to light in which the wavelength is very, very short, so high frequency light, right? And this extends beyond the range of frequencies of light that the human eye can see, right? So the human eye can only see from, let's say, reddish light to violet light, but to longer and longer wavelengths, we have infrared light and microwaves and radio waves, which are just light that just happens to have very, very long wavelengths. So the human eye can no longer see it, right? Just like you cannot hear a very, very low pitch, or you cannot hear a very, very high pitch, you cannot see light beyond the range that the human eye can see. But it's there, right? To the other end, to the high energy, the high frequency side, we have ultraviolet light and X-rays and gamma rays. These are all these fancy names are just simply light. It's just light of colors that go beyond the reach of our eye, right? So the importance of a spectroscopy, as I was saying, is that it allows us to measure how fast an object is moving away or towards us. And the reason this happens for galaxies in the universe is that if you think of a static universe that is not expanding, right? And you have Hubble looking at the universe down here in the Earth, and you have a galaxy, right, at a certain distance, right? Then you'll have this wave of light coming towards the observer, right? And no matter if the universe is static, no matter how far away the observer is from the galaxy, the light of the galaxy will always look of the same color, basically. It doesn't depend on how far away you are. If the galaxy is putting out blue light, you will see a blue galaxy, right? Now, if you have an expanding universe, right? If you have an expanding universe and the observer is sitting here, by the time this galaxy emitted this pulse right here, right? A small time lapse later, the galaxy effectively had moved away from the observer, right? So at the time it emits a second pulse, that would correspond to this pulse here, right? The separation between these two pulses, right, is longer, right? So, and the galaxy keeps on moving and moving and moving away from us, right, in an expanding universe. And the separation, and the further away the galaxy is, the faster it will seem to be moving away from us, right? So the larger would be the separation between these pulses, right? So what this translates into is that for galaxies that are very near you, right, you see the light to be when you take the light from those galaxies and you look how it's distributed among light of different colors, galaxies that are very near you look very similar to their intrinsic color, right? But galaxies that are further and further away, they all look redder. And they look redder because this electromagnetic wave, right, that's propagating the light, the wavelength of this wave gets longer and longer and longer, the further away a galaxy is. So this is a very powerful tool because in principle, right, in principle, if all galaxies had exactly the same intrinsic color, if all galaxies were the same and had the same color, we could measure the distance to a galaxy simply by measuring its color, right? If a galaxy looks red, it's because it's really far away, and if a galaxy looks blue, it's because it's very nearby, right? Now, it's not as simple as that, because not all galaxies are the same, and some galaxies are bluer and some galaxies are redder, right? And that depends on basically how old the stars are that live in that galaxy are, right? Older stars usually are redder, and younger stars are usually bluer, right? So if you see a red galaxy, it's difficult to know if it's a blue galaxy that's very far away, and that's why it looks red, or if it's really a nearby galaxy that's intrinsically red, right? So in order to overcome this, we use this tool that we call a spectroscopy, right? So in a spectroscopy, when you take the light that comes from a galaxy and you disperse it using some optical element in your telescope into light of different colors, right? You don't see a flat distribution, but you rather see something that looks like this, right? And you see this two-dimensional spectrum here. There are these vertical lines that are brighter, and there are also some vertical lines that are fainter, right? These all correspond to either emission or absorption lines that are associated with different chemical elements in the gas that's in between the stars or in the gas that's in the surface of the stars themselves, right? And I don't want to go into much detail about how these spectral features, these spectral emission and absorption lines come to be, but what's very important is that if this line here, for example, which is a line of oxygen, or that line there, which is a line of hydrogen, right? If that line, no matter what the color of the galaxy is, no matter if the galaxy is red or blue or green, right? That line will always have the same frequency or the same wavelength. That means that the light from that line always has the same color, right? So now we have a standard, right? And now we can take a spectrum of a galaxy. We can say, where is this oxygen line, for example, sitting, right? And depending on how much that line moves towards redder colors, right? The further away this galaxy is, that line is going to appear redder and redder and redder, right? But it's going to be the same for all galaxies. So simply by taking a spectrum of the light from a galaxy and measuring the position, the wavelength, or the color of a certain spectral feature in the spectrum, right, that we know, we can measure the velocity with which this galaxy is moving away from us, and therefore we can know how far away they are, right? So this is by far the most widely used method to measure distances of galaxies. Just take a spectrum of them and measure the distance using Hubble's law, right? So what I'm showing you here is a map of roughly 50,000 galaxies, right? These are roughly 50,000 galaxies over the whole sky, right? And now they're color-coded by their redshift, or they're color-coded by their distance, measured using this method, right? And you can see that you can immediately start to pick up, once you look at objects of the same colors, this filamentary structure with voids and walls that surround them, right? Now, very quickly, I want to go over the history of the universe and tell you how far away back in time we can actually detect galaxies and measure their redshifts and measure their distances, right? So, we now know that the universe started with a Big Bang, and that from the time of the Big Bang till today, roughly 13.7 billion years have gone by, right? So this bar here I'm going to use to represent the history of the universe, right? So first, by today, so 100% of the history of the universe, we have the Milky Way, which we live in, and we have all these old galaxies that I told you about that we can easily see when we take pictures of the sky. Some of them you can even see through a small telescope in your backyard, right? And when you take deeper and deeper pictures, we can make very detailed maps like the one I just showed you, which show the distribution of thousands and thousands and thousands of galaxies around us, right? And this filamentary structure already shows up in the local universe surrounding us, right? Now, if we go back to roughly 70% of the history of the universe, this means we observe galaxies at larger and larger distances until the time at which the light left from those galaxies corresponds to 70% of the history of the universe, right? We're seeing the universe as it was when it had 70% of its current age, right? So if we take deeper images, we can still see plentiful of galaxies, right? And we can use this redshift technique to measure their distances, right? And this map that I showed you before, in which we're sitting in the middle, right, corresponds to, you see how it starts fading out at larger and larger distances. It starts fading out because basically the telescopes that were used to build this map are not powerful enough to detect fainter and fainter objects further away, right? So by now, today, astronomers can build maps like this, very detailed distributions of galaxies, back into roughly 70% of the history of the universe. Now, if you keep on going, right, you can use maybe a bigger telescope, look at a smaller patch of sky, because you have to look for a very long time to see fainter and fainter objects, right? And you can still detect galaxies all the way easily, fairly easily today, all the way back to 50% of the history of the universe. The problem is that by this time, here I'm showing you just some examples, but by this time you start losing the ability to map this large-scale structure, right? To map this web of filamentary structure. Here I'm showing you some maps of galaxies, right? This is what you can see here is distance from the Milky Way, right? On a very small patch of sky, right? And in these maps, you can see that you can still pick up these filaments, right? But they start fading away once you reach roughly 50% of the history of the universe. So we can only see the large-scale structure up to that epoch. Now, if you keep on going, right, you can use maybe an 8-meter class telescope, the largest telescopes that we've built so far, right, to look at very small patches of sky, but for a very, very long time, and integrate your pictures for a very, very long time. If you do that, you can still pick up galaxies all the way back to when the universe had roughly 15% of its history. And by this time, you start seeing very interesting things. You start seeing that galaxies no longer look like this smooth ellipsoids or smooth disk that we see today, but they start looking more clumpy and distorted. And the reason is that you start seeing more interaction between little star-forming knots in the early universe. And you see these clumps of gas forming stars very quickly. So when you look so far back into roughly a 15% of the universe age, you can evidently see the difference between how galaxies were at that epoch and how they are today. And what you're seeing is basically the process of galaxy formation, right? Now, where's the limit today? So today, year 2012, right? The furthest galaxies that we can detect in the deepest images that we've ever taken with the Hubble Space Telescope live about, emitted the light that we're receiving, right, today, when the universe was had about a 5% of its present age, right? So we can see all the way back, we can see galaxies, and and this picture here, it's basically the same picture in the back, right? But taking in slightly different colors. And you can see these very, very faint smudges here. Those correspond to galaxies that look as they were when the universe had 5% of its current age. So we're seeing almost all the way back into the history of the universe, almost, right? Beyond that, our telescopes are just not big enough or not powerful enough to detect galaxies, right? And the only thing that we're left is with indirect detections, like what I'm showing you right here. So this shows you an image, right, of the sky in far infrared light. So this is infrared light that the human eye cannot see, right? But you can build a telescope and build a camera that can detect this type of light and take a picture, right? So a method that's been proposed, and it's very, very interesting, is that you can actually take this image and you can see, you can take all the objects that you can actually detect in the image, right? And remove them and subtract them from the image. And all you're left is with this halo of light, right? This diffuse background of light, which is corresponds to the sum contribution of all the objects, all the galaxies in that image that were too faint for you to pick up individually, right? So basically, that halo of light, that orange emission that you're seeing there, has some contribution from galaxies that are beyond this 5% epoch, right? So, but we cannot learn anything about them individually and about their detailed properties from data like this. So what we need to do is just build bigger telescopes in order to explore the universe further down. Now, the universe also gave us one of the most beautiful gifts, and that is something we call the cosmic microwave background, right? So basically it's like the universe is an adopted child, and we're supposed to know where he comes from, and the only thing we have, right, from this child, we don't know nothing about the history of his family, his biological family, but this child came with a picture of him when he was a baby, right? And that's all we have, right? So when the universe was at a very, very early stage, right, it was this big, dense soup of particles, right? So you have mainly subatomic particles and radiation photons in this dense condensed plasma, right? And it looked a little bit like this picture I'm showing you here on the left. This is a very simplified version of what it looked like. So you had these red big balls that are called protons, which are basically the nuclei of atoms, right, of hydrogen atoms, which is the atoms, the most common atoms in the universe, right? And you had these yellow balls here, which are electrons, right? And the universe was so dense and hot that the electrons could not bound and get together with a proton in order to form an atom, because they were just, the temperature is so high that the velocities of these particles were extremely high, right? So all the atoms, basically, or all the nuclei and the electrons in this early dense hot universe were floating around, right? And whatever light was traveling throughout this very dense universe, right, would eventually hit an electron. And electrons, when they're flying around free, they're very opaque to light, right? So when you have this fog, right, of free electrons floating around in the early universe, light cannot go through it. It just, photons of light just hit an electron and get scattered in some other direction, and you can never take a picture in this early universe because light just doesn't propagate, right? But the universe is expanding and is cooling down, right? And eventually it reaches a low enough temperature and low enough density for the electrons to start moving slowly enough to be captured by protons. Remember that protons have positive electric charge and electrons have negative electric charge, so they attract each other and they form atoms, right? So that process happened very, very sharply in the history of the universe, roughly when the universe had 400,000 years, right? So 400,000 years after the Big Bang, this called recombination, this recombination happened. And suddenly, all the electrons that were floating around in this fog got bound into these protons, and the universe became transparent. So this was like, when the universe had 400,000 years, it was completely foggy, no one could see anything, and suddenly, in a very quick lapse of time, the universe became transparent, right? And this radiation, this light, right, this image of the universe kept on traveling for billions or 13 billions of years, right? Until today we can detect it with our telescopes, right? And that is what this picture is. This picture shows you a photo of how dense were different parts of this initial soup of that was the universe when it had 0.003% of its current age, right? So this is very, very fascinating because we have a map of what the initial conditions were for galaxy formation. This tells us how clumped matter was at the time. Now, I want to move now to the way back, right? So we know now that we can detect galaxies further and further and further away to the limits of our technology, basically, right? But almost all the way through the entire history of the universe, right? So what have we understand from these observations about how galaxies form and how they evolve towards the galaxies we see today? So what's very important here is to understand the stage in which galaxies are forming, right? Galaxies are not forming in an empty universe, right? We have come to realize in the last few decades that actually what we call normal matter, so the stuff that you are made of, the stuff this room is made of, the stuff stars and galaxies are made of, only corresponds to a very small fraction of all there is in the universe, roughly a 5%, right? And then there's this other 70% that is in the form of this mysterious dark energy that I'm going to tell you about now, and this other 20% that is in the form of this mysterious dark matter that I'm also going to tell you about. So how is that we came to realize that we are so insignificant and that most of the universe is made of something we have no idea what it is, right? So the first evidence for the existence of dark matter came in the 1930s from a professor at Caltech whose name is Fritz Zwicky, right? So imagine the following. If you have a cluster of galaxies, like the one I'm showing you here, so this is called the Coma cluster of galaxies. So this is a bound group of many, many galaxies that are floating and are orbiting each other, basically in space, right? So if all those galaxies were static, were not moving, right? If they were just floating statically in space, right? The gravity pull between them would make the whole system collapse, right, into its center, right? So the only reason these galaxies are not all falling into the center of the cluster because of the gravitational force is because they're moving around, right? So they're moving around and they experience centripetal accelerations that prevent them from falling just the way a satellite orbits the Earth, basically, right? That the movement of the satellite prevents it from falling into the surface of the Earth. Here you have the same thing. So the more massive the cluster is, the faster the stars have to move in order to keep it in order to keep from falling into the center of the cluster, right? So what Franz Zwicky realized is that, well, I can take all these galaxies, I can measure how fast they're moving, right? And that should give me a rough estimate of how much mass there is in this whole cluster, right? When he did this experiment, he got a number that was 400 times larger than all the mass that he could account for by looking at the individual galaxies. So if you take the mass of all the galaxies in the cluster and you sum that up, that is 400 times smaller than the mass that there really is there, and that you need to explain how fast these galaxies are moving, right? So later in the 1970s, this was further confirmed. The existence of this mysterious dark matter that we do not see was further confirmed by looking at how inside a single galaxy stars rotate, right? So with inside a single galaxy, you have the same problem, right? You can have a galaxy, right? And stars are rotating around the center of the galaxy, right? So if the stars were standing still, they were not rotating, they would all fall down into the center and the galaxy would collapse. The reason that this doesn't happen is because they rotate fast enough in order not to fall, right? So if you take what's called a rotation curve of a galaxy, you just simply go to different distances from the center and you measure as a function of distance how fast in kilometers per second, basically, these stars are rotating around the center of the galaxy, right? You can measure basically how much mass there is in this galaxy, right? And when you do that, you get the same problem. You need roughly 10 times more mass than you can actually account for by just summing up all the stars and all the gas that lives in there. Now, there's further evidence for the existence of dark matter from a phenomena that we call gravitational lensing. Now, in Einstein's theory of general relativity, light follows straight lines in space-time, but space-time can get bent by the presence of mass, right? So the net effect is that you observe is that rays of light can actually be bent in their trajectory by the presence of mass. Now, when you have a giant, massive cluster of galaxies in space, and you have a galaxy behind it, right, this cluster, a ray of light that's passing by the cluster can actually be bent, and its trajectory can be changed into the direction of an observer, let's say, with a telescope here on Earth, right? So the net effect of this is that if you have an object that's perfectly aligned behind the cluster, right, you would see basically a ring of light around the cluster, right? And we observe this, right? This is a picture, a real picture of a cluster of galaxies. And you see all these objects that are kind of distorted and bent like little arcs, right? So these objects are not members of the cluster. They're galaxies that lie beyond the cluster, whose light is being bent, right, by the mass in the cluster, right? Now, you can make a model and predict, depending on how much mass there is in this cluster, right, you can predict by how much the images of these galaxies will get distorted, right? When we do that, you also find that in these clusters have much more mass than we can really account for, right? So we have many different lines of evidence telling us 90% of the mass in the universe, right, we cannot see, and this is what we call dark matter. But we know it's there, right? So roughly 80% of the matter in the universe, it's unaccounted for. This is what we call dark matter, right? But that's not all there is, right? There's another big mystery, another big important component. That's what we call dark energy, right? So how did we came to learn about dark energy now, right? So people, since Hubble discovered the universe was expanding, people ask themselves many times, is this expansion constant? Is the universe always expanding at the same rate? Or is this expansion changing with time? Is it slowing down? Is it getting faster, right? So you can think of different universes. This is the axis of time, in which the universe can get bigger and maybe collapse again over itself. So the expansion would accelerate, and then the expansion would eventually decelerate, right? Or the expansion could reach a constant and keep on expanding at the same rate, right? Or maybe the expansion is actually accelerating, right? And moving, and the universe expands at a faster and faster and faster velocity all the time. How do we go about measuring this, right? So this is fairly simple to measure, right? If you remember Hubble's law, it was a relation between the distance and the velocity of galaxies, right? So if the universe expands always at the same velocity, you just expect to see a tight relationship between the distance and the velocity of galaxies. That would look something like that. Now, if the universe was decelerating, right, that means that faraway galaxies that you see more in the past, you see at earlier epochs in the universe, right, should appear to be moving faster because the universe was expanding faster in the past, right? It is decelerating, it's expanding slower and slower and slower, right? On the other hand, if the universe was accelerating, right, and you look at very, very distant galaxies, they should appear to be receding slower, right? Because galaxies are moving faster today. The universe is expanding faster today, right? So in the past, when you look at the very distant galaxies, they should appear to be moving slower than if the velocity was a constant, right? If the expansion was constant, right? So in 1998, this was observed for the first time by two different teams at Harvard and Berkeley. And this is what's basically considered the discovery of dark energy. So teams led by Adam Rees and Brian Schmidt and Saul Perlmutter at Berkeley, they used a method based on supernova explosions for which you can measure the distance very accurately, right? To actually plot this relation and measure very significantly that the universe was actually, the expansion of the universe was actually accelerating, right? This earned them the Nobel Prize in 2011 because of this discovery. So, yeah, we know the universe now, we know is expanding, and we know that expansion is accelerating, and it's going faster and faster and faster. The problem is we have no idea why, right? And this is one of the biggest puzzles of today's astronomy. We have no idea why the universe is accelerating. So one possibility is that we have a mysterious energy component in the universe, which is what we call dark energy, right? And it should be accounted to roughly 70% of all the energy in the universe would have to be in this component in order to explain the observed acceleration. But it's very important to keep in mind that dark energy is not it's not a type of energy that we have detected. The only thing we have seen is an accelerated expansion of the universe. So dark energy, as I said at the beginning of the talk, the word dark means ignorance. It doesn't mean it's dark. It might not be dark. It might not even be energy. We have no idea what's causing this expansion, right? But we know it's happening, right? All right. So now that we understand the stage, right, we can actually try to understand how galaxies form in this large scale, in large scales in the universe, right? So we know that the bulk of the matter and the gravity is dominated by this dark matter component. We know how much of it there is in the universe. And we know that we also have this dark energy pulling the universe apart and making it accelerate faster and faster, right? And we also have a picture of the baby universe that tells us how dense and what was the typical size of the initial clumps of matter in the universe. So we can put these three pieces of information in a computer, right? We can put these three pieces of information in a computer, right? And we can say, okay, let's throw in the amount of dark matter that we think there is, and let's make the universe expand accordingly to the amount of dark matter and dark energy that we think there is. And let's clump the initial conditions to the scales and sizes that this baby picture of the universe in the cosmic microwave background tells us that it should be, right? And when we do that, we can actually run a simulation of how would matter evolve and behave and move in the universe. And this is fascinating because when we do that, we realize that matter tends naturally to clump in this large-scale filamentary structure that looks exactly the same as the way galaxies are distributed in space, right? So this is one of the largest triumphs of 20th century cosmology, right? To be able to reproduce the large-scale distribution of galaxies in space, right? Now, it's not only about explaining the distribution, but it's also about explaining how galaxies form, right? How galaxies themselves form. Now, in this large-scale distribution, which is completely dominated by dark matter, there is a trace of normal matter in the form of gas, right? So a big area of understanding the formation and evolution of galaxies is to understand how does the gas that it actually will form the stars and will eventually form the planets and the people and everything else moves inside this dark matter distribution, right? And a lot of work has been done in this regard over the last 20, 30 years, right? Since we understood this large-scale hierarchical formation of galaxies, right? And here I'm just showing you a pretty picture of how gas eventually falls inside a little dense knot in this dark matter distribution. So what happens is the universe is expanding, right? And gas is living together with dark matter in this filamentary structure, right? Now, some parts of the universe, some knots in this web of dark matter are dense enough to pull all the gas surrounding it and decouple it from the overall expansion. So all the gas is expanding and getting thinner and thinner and thinner, less dense, right? But if you have a very dense knot, you can have what we call collapse, where basically most of the gas surrounding that knot would eventually, because of the pull of gravity of that dense knot, would fall into this dense knot. And once it starts falling, right, it can cool down and it can reach very high densities. And eventually it can form stars, right? And once this collapsed, colder gas is able to form stars, then we have the birth of a galaxy. But galaxies then don't live in isolation. Right next to them, there are other galaxies that are also forming. So then you can also have all these little star-forming clumps coalescing together to form larger and larger and larger galaxies in the densest knots of this web, of this what we call the cosmic web, right, which is this large-scale distribution of dark matter. Now, here, this is probably the last pretty picture in this talk. So, here, what I'm showing you is, okay, we just looked at one galaxy, right, and how it formed. So what happens if we take the dark matter distribution and we add all the physics that govern the movement of gas and the formation of stars from that gas? And not only that, but also the reaction, the effect that newly formed stars have on the gas, right? Which that is something very important in galaxy formation. You form a galaxy, but that galaxy has an effect on its surroundings, and it can heat up, and it can introduce a lot of energy in the gas surrounding it, right? So this is one of the latest simulations of large-scale galaxy formation, basically. When you put all the physics together in large scales in this cosmic web of dark matter, and you're able to reproduce very accurately the overall distribution and properties of the galaxies that you form, right? So, as I was saying, galaxies here, this is just a pretty picture from one of these simulations where in pink you see the overall dark matter distribution, and in white you see the galaxies, right? So if you zoom in a little more and then keep on zooming in, you see that in the densest knots of the dark matter distribution, that's where galaxies actually form and live, right? So the big picture, to summarize, basically, is that after the Big Bang, some 400,000 years after the Big Bang, we have this image that we call the cosmic microwave background, which shows us how matter was distributed and clumped in the very early universe. Now, that matter, by the effects of by a fight between collapse induced by gravity and the expansion of the universe, it starts forming the cosmic web, which is this large-scale filamentary structure of dark matter. And in the dense, so you have a period that we call the Dark Ages, in which you're forming all this structure, but no galaxies exist yet, right? And then at some point in the densest knots, right, the density is so high that they can actually collapse, and the gas can infill into the densest knots in the structure, right, and form galaxies, right? And that's why galaxies trace the overall distribution of dark matter. And then you form the first galaxies, and then they evolve throughout a series of very complex processes, all in shape and properties, all the way into the galaxies that we see today. And this evolution is going to be the main topic of Rick Williams' talk about a month from now, in the second part of this lecture. Now, finally, I just want to show you where the next frontier is, basically. What are astronomers going to do about studying the evolution and formation of galaxies during the next 10, 20 years, right? So one issue is that I show you that we can make these beautiful maps of how galaxies are distributed all over the universe in large scales, only out to where the universe had roughly 70% of its current age. But in the very early universe, let's say about when the universe had 15% of its current age, we can only detect a handful of galaxies. And it's extremely difficult and futile with the current data to try to study how these galaxies are distributed in space, right? It's very, very hard. And trust me, because I tried. So all we need is more and better data, right? So one project that I currently work on, and it's going to be, I think it's going to be of great value in the next decade, is called the HEDDEX project. And what we're doing is we're basically using a new type of instrument that we have built on a large 9-meter telescope in McDonnell Observatory in Texas, right, to measure the redshifts of roughly 1 million galaxies, but not in the local universe, but when the universe had roughly 15% of its current age. So remember I told you a map like this map had roughly 300,000 galaxies, right? So you're going to be able to build maps like this, or even better than what you're seeing here, but in the very, very early universe. And that's going to allow us to understand way better how this structure, his large-scale structure in which galaxies live, evolves throughout time. The other big gap in our understanding comes from this period right here, right? So we have the picture of the baby universe, right, at the very, very beginning, but we only have a handful of galaxies that we can detect back into when the universe had 5% of its current age. So we don't know anything in between these two epochs. And this is by far the most interesting epoch, because this is where galaxies first formed, right? So if you want to see the formation of the first galaxies, you have to look into this epoch right here, right? And the only way to look into this epoch is to build bigger and bigger telescopes. So I'll just show you, I'll just go over a showcase of what are the main large telescopes that are currently planning to build. So there's the Giant Magellan Telescope, which is being led by the Carnegie Observatories. It's a consortium between many universities and institutes and countries, actually, Australia and Korea. But it's been led from the Carnegie Observatories. So this is a telescope that's composed of 7 mirrors, and each of these mirrors is 8.4 meters in diameter. So each of these mirrors is basically the size of the largest telescopes that we have today, right? So you put 7 of those mirrors together, and you build a telescope that's 25 meters across, right? This, when built, will be the largest telescope in the world, right? And it would help us a lot in order to start detecting and studying galaxies in this epoch, right? This is being built in Chile at the Las Campanas Observatory. The other big project is being led by Caltech, and it's called the 30-meter telescope. This is also a large collaboration between many institutions and many countries, right? And the 30-meter telescope is a very different concept. This has many smaller mirrors. This has roughly 500 1.5-meter mirrors, and they're all tiled together in the mosaic in order to build a large 30-meter telescope. And this will be built in Hawaii, in Mauna Kea. Now, the third giant telescope has a very original name, and it's called the European Extremely Large Telescope. Right? So the EELT, or European Extremely Large Telescope, is also going to be built in Chile, in the northern desert in Chile, in the Armazones mountain. And it's a similar concept to the 30-meter telescope. So you have, it's a big mosaic of small, roughly 1.5-meter mirrors. The only difference is that it has 2 times as many mirrors. So it's going to be almost a 40-meter telescope. The current design is a 39.5-meter telescope. So there was, at the beginnings of this project, there was talk about calling it the 40-meter telescope. And I think they're very thankful they didn't, because they had to scale it down, and they're in 39.5 now. So they could not use the name if they had used it. But this is also going to be built during probably by the end of this decade. Now, out of these 3 telescopes, the Giant Magellan Telescope, which is being led by Carnegie, is the project that's most advanced in its construction. And last Friday, there was an event at the Las Campanas Observatory, which is owned by the Carnegie institution, right? In which what we did was basically blow up the cap of the mountain, right? So if you want to build a telescope, first you have to make the peak of the mountain completely flat, right? So I want to show you a video right now, which is just an excerpt from the ceremony that happened last Friday, in which what you'll see is the peak of the Las Campanas mountain being completely blown out by explosives. So it's a fun video. Oops, what happened? There you go. Let's see. Play.
In a few moments, we will join our efforts to make this explosion happen by counting down toward the Big Bang. I'll let you know.
There you go. And kaboom. So you see, it's not a minor engineering task to just blow up the whole top of the mountain. You need a lot of explosives and then a lot of bulldozers and trucks to just dump all that dirt off the side of the mountain to be able to make a flat enough area, a big enough area to build your telescope on. But yeah, that happened last Friday in Las Campanas. So finally, the other big improvement that we're going to have in terms of resources in the next decade is what is called the James Webb Space Telescope. So So this is, as you all know, the Hubble Space Telescope has been the main workhorse for studying the distant universe over the last 2 decades, almost, since 1993, when it was launched. But the Hubble is only a 2-meter diameter telescope. It's a fairly small telescope. But it has the advantage that it lives in space, so it's not affected by the atmosphere, right? So looking through the atmosphere, the best example someone gave to me is, look, if you're an astronomer, you have a telescope and you're looking through the atmosphere, it's the same as looking down from the bottom of a pool, right? So when you're underwater and you look up, all you see is this blurry stuff, right, beyond the surface of the water, right? The same thing happens with the atmosphere. So if you put a small telescope outside the atmosphere in space, you can resolve much finer detail and see much finer things that you can do from the Earth. So the James Webb is going to be a 6.5-meter space telescope that will be launched at the end of this decade. And it's also going to imply a major improvement, and it will grant us access to this very interesting time in the history of the universe. So that is it. I'll invite you all to come back on April 30 to see Rick Williams' talk. So I hope I gave you a good idea of how galaxies manage to form, and Rick is probably I'm sure going to give you a really good idea of, once galaxies are formed, how do they evolve in present-day galaxies that we observe all around us. So thank you.
Okay, we'll take a few questions. Let's see, we'll start right here.
All of the earthbound telescopes are being built in earthquake-prone areas.
Yes.
Is this being taken
Yes.
into consideration?
Yes. Yes. So the main driver for building these telescopes, of course, is atmospheric conditions, right? So, I'll repeat the question. He's asking me, why are all these large telescopes being built in areas that are very, very shaky in terms of earthquakes, right? So this is, of course, a very delicate matter, because if you have a big earthquake, you don't want your billion-dollar telescope to break, right? So the main driver for choosing the sites for the telescopes is atmospheric conditions. You want to have the best possible conditions to observe all year round. So you want to have a place that's clear most of the time, that has very low water vapor in the air, and also you want to have a special geographical and atmospheric conditions regarding winds that will promote a very stable atmosphere with very laminar winds that will provide a very good image quality, right? Now, of course, very, very detailed modeling. The engineers that build this telescope go into a lot of effort to do very detailed modeling of what would happen to these large structures in the case of a big earthquake, right? And all the specifications for these telescopes consider this, and they're all designed to sustain very large earthquakes without suffering critical damage, right? And there's a fact that helps you a lot, and it's that when you're sitting in the top of a mountain, a lot of the energy gets dispersed before it reaches to the peak of the mountain, right? So if you put the same telescope in the ground, let's say, I mean, Chile suffered a big earthquake yesterday, right? I'm from Chile, so I know, I've had earthquakes my whole life, right? So if the telescope were in the ground, the damage it would suffer would be much larger than if it was in the peak of a mountain. And that helps you a lot in that respect. But this is all taken into account. Yeah, so he's asking, when are black holes formed in this timeline of galaxy formation? So that is actually a very, very important important question, and it's currently a big unknown. There's a lot of research going on about the formation of the first black holes, right? So over the last decade or two, we have come to realize that almost every galaxy in the universe, or at least all the massive galaxies in the universe, host a supermassive black hole in its center, right? And even more, we've come to realize that if you measure the mass of that supermassive black hole that lives in the center of galaxies, it is very much related to the mass of stars around it, in the spheroidal components of galaxies that surround these black holes. So it seems like black holes are actually the evolution of black holes is very tied to the evolution of galaxies themselves, right? And so we need to have a theory to explain, given the black holes we see today, given the mass they have, and given the rates at which we observe them to feed, right, over when we look further and further back in the past, right, we need to form a certain amount of black holes, a significant amount of black holes, very early on in the universe. And we need them to form in order to have, and the formation mechanism has to make them have a high enough mass that makes it very challenging for today's theories, right? So we currently do not understand exactly how black holes are formed in the early history of the universe. And there are mainly two schools here, right? One is in the very early universe, the type of stars that you form are very, very large and massive stars. There's a chemical reason for this that has to do with the fact that to form a star out of a cloud of gas, you need to cool down all that gas, right? So chemical elements like oxygen and nitrogen, etc., they emit a lot of light in these emission lines that I show you. And this removes a lot of the temperature, a lot of the energy from the clouds of gas, right? So when you have, the more chemical elements you have, heavier elements, the easier it is to cool these clouds down, right? So you can take basically a small cloud, right, which doesn't have a lot of gravity, doesn't have a lot of gravitational pull because it's not very massive. But if you have these rich elements, you can cool it down fairly easily. Now, in the early universe, there are no heavy elements. They haven't formed yet, right? So you don't have this coolant, basically, in the clouds, in the big clouds are forming the first stars. That means that in order to form a star, you have to have a very, very, very big cloud of gas. So it has a mass that will promote a very strong gravitational pull, right? So the first stars are thought to be very, very massive. And these massive stars could basically live very short time spans and explode in supernova explosions and form in these supernova explosions, form the very first black holes, which could be very massive, right? And then the other school is that in reality you form more normal stars that do not produce these very, very massive black holes, but there are mechanisms that allow you to merge these many smaller black holes that you form early on into these big black hole seeds that you need to explain the black holes we see today. Yeah, that was kind of a long answer, but yeah, sorry.
You talk about dark energy, and I'm a chemical engineer, and I always talk about entropy. Nobody ever knows what entropy is. Aren't they really basically a measurement of the same thing, of which nobody knows what either one is?
I don't know. Yeah, I mean, dark energy is really fascinating in that respect. I mean, I think it's very important to stretch the point that dark energy is nothing more than a name to an observed phenomena, which is the accelerated expansion of the universe. So, yeah. So, I mean, there are three main possibilities here, right? One is that, yeah, there is this weird, mysterious energy component that embeds the whole universe and actually makes the universe expand, right? But another option here also is that maybe our understanding of gravity is completely flawed, right? So maybe gravity doesn't work the way it is, right? Because dark energy, the observation is basically the expansion of the universe is accelerating, and we do not expect that from a universe that only contains matter, right? So if you only have matter, basically matter is pulling other matter, right? And eventually the expansion of the universe should decelerate, right? Or at least reach a velocity where it stays constant, right? But maybe what happens here is not that there is a dark energy, but what happens here is that we don't understand how gravity works. Maybe gravity loses strength at very large distances, or maybe gravity reverses its sign at very large distances, or we have no idea. All right, these are all speculations, right? So you shouldn't take them seriously at all. But the truth is, we only observe a phenomena, and we don't know what's going on.
I'm going to stop you before you give away too many secrets.
But I'm sure he'd be happy to answer questions. So I know there's some people who have more questions. Feel free to come on up. We'll see you in 3 weeks, April 16th.